A warm welcome again to the Kiel Image Seminar. It's a great to have you all here today. We have a fantastic speaker today. It's my pleasure to introduce you to Sergey Sviyazov. So Sergey completed his master degree in physical chemistry at Novosibirsk State University in 2022. He is currently completing his PhD under supervision of Professor Igor Koptyok and Dr. Dudari Bruneva at ITCSB RAS Novosibirsk. During his PhD, Sergey spent part of his research at the University Medical Center in Freiburg under the supervision of Dr. Andreas Schmidt. His research interests include fundamental aspects of nuclear spin, isomers, and advancing parahydrogen-based NMR hyperpolarization techniques towards biomedical applications. After the talk, we have time for questions, and with this, Sergey, the stage is yours.
Okay. Hello, everybody. And first of all, I would like to express my gratitude to be here today. I will discuss my PhD and master way in Novosibirsk. Yes, I am from International Tomography Center from Novosibirsk. My supervisors are Dudari Burueva and Igor Koptyuk. And my topic today is parahydrogen-based hyperpolarization techniques for a wide range of application. And let's start. Nuclear magnetic resonance and magnetic resonance imaging are widely used in modern chemistry and physics. However, these methods have a significant drawback associated with low sensitivity, but there are a lot of hyperpolarization techniques that can overcome these problems by creating a non-equilibrium population among nuclear energy levels. So there are a lot of hyperpolarization methods, but interesting for me is, and for my lab, is method based on parahydrogen. One of the promising is parahydrogen-induced polarization, or PHIP. This technique use parahydrogen. Parahydrogen is nuclear spin isomer of hydrogen with total nuclear momentum equal to 0, and parahydrogen used in these techniques as source of nuclear singlet order. So parahydrogen in itself is invisible in NMR method, but one can use catalytic reaction for add parahydrogen to some unsaturated bond, and in this case, breaking symmetry yields to strong NMR signal in products of this reaction. But one important thing for PHIP, it's requirement of pairwise addition. Pairwise addition is necessary for observing of this effect, and we can observe this effect due spin order of hydrogen is partially preserved in the product of hydrogenation, and we can see enhanced signal from protons from parahydrogen. PHIP has two main modes, Pasadena mode and Altadena mode. In Pasadena mode, the reaction is carried out in high magnetic field, as a rule, field of NMR spectrometer. And Altadena mode, in this mode, the reaction is carried out in low magnetic field, as a rule, in Earth magnetic field. In general, parahydrogen-based techniques in general, and PHIP in particular, has a lot of applications. The most important, I guess, is real-time monitoring of metabolism. For example, we can polarize pyruvate and monitor conversion of pyruvate to lactate in tissue, cell, and animals. There are a lot of works and literature devoted to this application. But there are other applications, for example, mechanistic studies of catalytic reactions. We can use PHIP for mechanistic studies of homogeneous reaction and for heterogeneous reactions. Okay. So I started my work in this field from application of PHIP for heterogeneous catalysis, and my first work about interesting catalytic system. Recently it was proposed palladium supported to nanodiamond with defect graphene shell. This catalyst is perspective for selective hydrogenation of acetylene. It's a really important process for industry. And this catalyst has two main forms. First form with monoatomic distribution of palladium atoms. You can see here, so is support, and it's palladium atoms with monoatomic distribution. And second form with cluster distribution of palladium. You can see here cluster distribution of palladium. So in original work of our Chinese colleagues, it was shown that form with monoatomic distribution has remarkable catalytic activity in selective hydrogenation of acetylene, and moreover has really good stability over time, unlike our single-site catalysis. For single-site catalysis is unlike good stability over time. We used this catalysts for selective hydrogenation of propyne to propylene, and we compare the main catalytic characteristic and single enhancement factor for protons of propylene. And so we observed high selectivity, and reaction starts at low and at high temperature for catalyst with monoatomic distribution. At the same time, we observed low selectivity, and reaction starts at low temperature for catalyst with cluster distribution. But the most important for us that single enhancement factor was almost 6 times bigger for catalyst with monoatomic distribution, and it's logical because for such catalyst we can expect mechanism of reaction like homogeneous catalysis, and in homogeneous catalysis is typical to pairwise addition. So in general, for heterogeneous catalysis, pairwise addition is unlike and non-characteristic. So it was interesting work about heterogeneous PHIP. Next, the main part of my PhD devoted to using PHIP for enrichment of ethylene nuclear spin isomers. Actually, ethylene has 4 nuclear spin isomers called AG, B3G, B1U, B2U. So these symbols connected to this symmetry of wave function of nuclear wave function of ethylene. Note that these isomers have different special symmetry. It's important. There are 2 types, G symmetry and U symmetry. Also, you can see here population for statistic mixture of nuclear spin isomers of ethylene. Here, it's statistical population. So there are a few techniques for enrichment of nuclear spin isomers, but it recently proposed for ethylene chemical synthesis technique. In this technique, parahydrogen add to acetylene molecule in reaction of selective hydrogenation. And in this case, we have non-equilibrium population of nuclear spin isomers of ethylene. For example, no nuclear spin isomers with total momentum equal to are formed. It's connected to this using of parahydrogen. Parahydrogen has zero total nuclear momentum. Moreover, in our work, we showed that distribution of nuclear spin isomers for ethylene depends on stereoselectivity of hydrogenation reaction. Actually, if we will have syn addition, we will produce only Z ethylene. And if we will have anti-addition of hydrogen to acetylene, we will produce only E-ethylene. And for pure E-ethylene or Z-ethylene, we will have absolutely different distribution of isomers. For example, we don't have B2U for Z-ethylene, and we don't have B3G for E-ethylene. But also important thing is a ratio between isomers with different spatial symmetry. And you can note that for pure Z-ethylene, this ratio is same for statistical mixture, unlike E-ethylene. For this technique, we need to use a catalyst with pairwise addition of hydrogen, because only in this case we will observe effect. So we try to use first immobilized catalyst of rhodium and iridium, because we're perspective for this regard. And we tested three types of catalysts, and we found that for this catalyst, actually it's iridium complex supported to silica. We found a complex pattern in gas phase after carried out a reaction acetylene with parahydrogen over this catalyst. So we found this complex pattern, associated with enhanced signals from ethylene molecules with one carbon 13 label. So we measure maximum observed signal enhancement, and it was equal to 140, and corresponding polarization level 1.7%. So, and also interesting thing that pattern that we can see in NMR spectra depends on stereoselectivity of hydrogen addition. We did simulation, and for Z-ethylene, in the case of syn addition, we have this pattern: absorption, emission, absorption, emission. And for anti-addition, we have absolutely another pattern: absorption, 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 emission, emission. So we compare our experimental spectrum with simulated spectrum, and we concluded that syn addition occurs our catalyst. So it's interesting information for mechanistic studies. Later, we used our two catalysts for this reaction. It was bimetallic palladium indium catalyst supported to aluminum oxide, and palladium catalyst palladium supported to titanium oxide. So this catalyst used for heterogeneous PHIP is more or less popular for this regard. We tested all catalysts in reaction with parahydrogen, reaction acetylene with parahydrogen, and measure the main catalytic characteristic. So you can see here. But more important for us is observing of enhancement. And in general, in the case in ethylene, where protons from parahydrogen located in symmetric positions, and we cannot see any enhanced signal. And for observing of enhanced signal, we need to conduct symmetry broken reaction. And for this regard, we add bromine to ethylene. So actually, it's reaction of bromine addition, and we have bromoethanol. And in bromoethanol, protons from parahydrogen are not in the same symmetric positions, and we can see enhancement. So from bromoethanol, we saw good signal enhancement in proton spectra. And the best was for immobilized radium catalyst. And so another important thing that pattern of signals from bromoethanol also depends on stereoselectivity of hydrogenation reaction. And for example, for pure ethylene, we have this pattern. For pure Z-ethylene, we have this pattern. So we understand it using simulation of hyperpolarized spectra from bromoethanol, and we compare our experimental spectrum with simulated experimental spectra, and concluded about percent of scene addition for each catalyst. For example, for iridium, immobilized iridium catalyst, we observed almost 100% scene addition. For palladium-indium catalyst, we observed 92% of scene addition, and almost 50% for palladium supported to titanium dioxide. So it's also interesting information for catalysis. But for us, the most interesting thing is characteristic time of interconversion between different classes of nuclear spin isomers of ethylene. So for a study interconversion with storage gas after hydrogenation reaction in syringe for some period of time, for variable period of time, and we observed dependence between enhancement level of bromoethanol on storage time. So we approximated our dependence using mono-exponential decay, and we concluded that this decay corresponds to equilibration process within classes of isomers differing in spatial symmetry. I mean that this decay corresponds to process equilibration between AG and B3G and B1U, B2U. So with same spatial symmetry. We understand it when we used iridium immobilized catalyst, when we used for same thing other two catalysts, we observed bioexponential decay, and T-short from this decay was also same to this case, and we conclude so T-short corresponds to these processes, and we concluded that T-long from bioexponential decay corresponds to interconversion of ethylene nuclear spin isomers with different spatial symmetry. So interconversion between G and U classes. Okay, finally, the main results of this part of work was understanding of characteristic time of interconversion nuclear spin isomers of ethylene with different symmetry. So for process interconversion with same spatial symmetry, characteristic time is like several seconds from approximation. And for interconversion between isomers with different spatial symmetry, in characteristic time of interconversion was a few thousands of seconds. So it's really a lot for protons. It's really long-lived states. There are 4 publications about it devoted this project. Okay, part 3 of my report today is hyperpolarization of different substrate using PHIP-SABRE approach. It's also was important part of my PhD, like my last years. So PHIP is really important technique, and PHIP can be used for hyperpolarized biorelevant molecules, for example, fumarate or succinate. But the PHIP has really significant drawback connected to for PHIP is necessary the presence of unsaturated precursor of target molecule. For example, pyruvate does not have unsaturated precursor E, and we cannot polarize pyruvate using standard or conventional PHIP approach. But recently it was proposed by Ranieri PHIP-SABRE procedure, and key idea of this procedure is one can design of unsaturated precursor and so add alcohol moiety to carboxyl group of target molecule, and there is only one requirement for these techniques to molecule should have carboxyl group, but we know a lot of biorelevant molecule have carboxyl group. It's okay. So after if we have precursor, we can use this precursor to hydrogenation reaction. We can add parahydrogen to this unsaturated side arm, and after that we can use spin order transfer for transfer polarization from protons to target heteronuclei. As a rule, it's carbon-14. After it, we can hydrolyze our molecule to remove this side arm, and in this case, we can have hyperpolarized target molecule with polarization on heteronuclei. So it means polarization can live a lot of time, like 1 minute at least. Here you can see general experimental protocol of PHIP-SABRE procedure that we used. We started always from precursor. Here I used scheme for acetoacetate as an example. So initially we have precursor. We add parahydrogen to this precursor. As a rule, we used to high temperature and used rhodium catalyst. After it, we used spin order transfer. So we used magnetic field cycling or linear B0 sweep. In linear B0 sweep, we swept linearly magnetic field from magnetic field about about 30 nanotesla to several hundreds of nanotesla. In magnetic field cycling, we did almost same thing, but Actually, we transferred a sample directly after hydrogenation to magnetic shield with specific magnetic field inside it. And after it, we get out our sample slowly from this magnetic shield. So we did it manually in magnetic field cycling. It's important thing. So after a singlet order transfer, we hydrolyze our molecule and had target molecule. So we have hyperpolarized 4 molecules in this work: nitrate, acetoacetate, formate, and hydroxybutyrate. Here you can see precursors. All precursors were synthesized by Nikita Chukhanov and Nazim Mustafin in our lab. So let's discuss each substrate. So formate is perspective substrate because formate can be used for metabolism studies, at least for plants, moreover, formate can be used as a standard for ZUF NMR. So it's interesting to hyperpolarize it. And here you can see summary of our work with formate. Actually, it was article, but it's only a summary here. So first of all, we optimized hydrogenation procedure. We had good level of proton polarization. After that, we did spin order transfer using MFC, and we observed actually low polarization of carbon 15, and finally we did hydrolysis using basic solution. So the main question to this work is why we have really low polarization on carbon 15. Probably it's connected to strong J coupling between this proton and this carbon, and due it a lot of polarization was during faster oxidation on this proton. So the main conclusion of this part of work that the presence of the strong J coupling quickly leads to rapid relaxation of carbon 13, and it's really important and consequently to its loss during SOT procedure. So the polarization transfer procedure for such groups is limited by rapid relaxation. Next interesting substrate is nitrate, because nitrate also can be used for metabolism study. It's an important part of metabolism for plants, and not only for plants, but also nitrate is really important for industry. It's used in a lot of industrial reactions. So understanding of mechanism of this reaction is really important for development of industrial processes. So our summary for nitrate, we optimized hydrogenation procedure. We observed really good polarization on protons and more or less good polarization of nitrogen after SOT. It was hard to optimize hydrolysis because hydrolysis for nitrate has not so typical mechanism like SN2, and we need to use a complex solution for hydrolysis in this case. So the most important thing here is we used for first time FIPSAC procedure for hyperpolarized of nitrogen nuclei. Actually, it was first time. So the results, it was demonstrated that FIPSAC strategy can be employed for hyperpolarization of nitrogen compounds. And it's really interesting thing and really new. So next perspective substrate is acetoacetate. It's important because the rate of conversion of acetoacetate to hydroxybutyrate depends on redox status of mitochondria, and redox status in mitochondria is really important because it can be shifted due to some disorders like cancers or heart disease. So we can use hyperpolarized acetoacetate as a marker of redox status in mitochondria, and there are several works using hyperpolarized by DDMP acetoacetate that show possibility of imaging cancer. It's interesting. So our summary for acetoacetate, actually hydrogenation is thought not so interesting, but hydrolysis is really important thing here, because in a standard mild condition that we used as a rule for our substrates does not work for acetoacetate. In this case, we observed only formation of inolate form of acetoacetate, and inolate form limits the rate of hydrolysis. So in standard conditions, we saw only inolate. It's the reason why we moved to harsh hydrolysis. First of all, we tried to use basic hydrolysis in harsh condition. Harsh, I mean high temperature, high concentration of basic solution, high pressure. So in this case, we observed formation of hyperpolarized acetoacetate, but at the same time, part of inolate remains unreacted, and moreover, partial decomposition of acetoacetate into acetone and carbonate is also observed. And finally, moreover, we observed maximum polarization of carbon-15. About 0.5% is really low, because inolate has short T1. You can see here it's T1 for inolate, and it's really short in comparison with our substrates. So we lost a lot of polarization during this procedure, because hydrolysis require a lot of time, like 60 seconds. For example, for pyruvate or for formate, we need only several seconds. Here we need 60 seconds, and at the same time we observed decomposition. We also tried to use acidic hydrolysis, but in this case we observed only rapid decomposition of allyl acetoacetate in acetone and CO2. And moreover, signals from acetoacetate are not observed, so it's not good. So hyperpolarized acetoacetate was produced via PHIP approach for first time, but hydrolysis of its ester proceeded only at harsh conditions and was accompanied by significant decomposition of the target salts due to heating. And our results for hydroxybutyrate is also interesting, because reaction between acetoacetate and hydroxybutyrate is goal for imaging. So we can also hyperpolarize hydroxybutyrate. And yes, for hydroxybutyrate, we observed really fast and full hydrolysis. We needed only 5 seconds for it, but at the same time, we observed a really low polarization on carbon, and probably it's connected with strong J coupling between this carbon nuclei and this proton, like to formate. So we also lost a lot of polarization during SOT procedure due rapid relaxation on the proton. So, and finally, for hydroxybutyrate, we also hyperpolarized hydroxybutyrate for the first time using PHIP procedure, but we have similar issues like formate with loss of polarization. Okay, we have one publication about it and one ongoing publication, 2 manuscripts currently in preparation. And my final part devoted to preparation of biocompatible aqueous solution of hyperpolarized metronidazole. So another interesting techniques, parahydrogen-based techniques, is signal amplification by reversible exchange approach. Key idea of this approach, the nuclear spin order of parahydrogen can be transferred to a substrate nuclei through network of J coupling in the intermediate iridium complex. So we add parahydrogen to iridium complex, and here through J coupling, polarization can be transferred to nuclear of substrate. Actually, SABRE can be used for polarization a lot of substrates, but one of the interesting substrates is nitroimidazoles, because we know from literature nitroimidazoles is a hypoxia sensor and can be potentially used for imaging of hypoxia for tissues under hypoxia conditions. And metronidazole is nitroimidazole. And for metronidazole, was a lot of efforts to hyperpolarize it, and there are a lot of works about it in literature, and actually really good polarization levels. But the main problem of this approach, this approach employs methanol as the solvent, and we need to purify final solution from methanol because methanol is not biocompatible. So we suggest to use cache-SABRE approach for hyperpolarize of metronidazole. The cache-SABRE approach involves hyperpolarization of substrate in biphasic system of core forming water. The sense of this approach is the substrate is polarized in the organic phase, and after polarization, the substrate is extracted to aqueous phase, and the substrate can be soluble in both phases, organic and water phases, but the SABRE catalyst is soluble only in the organic phase. So after optimization of this procedure, we had the best reproducible results, about 2.3% of polarization on nitrogen nuclei for this concentration of metronidazole in the aqueous phase. So it's really good signal enhancement at the biomedical relevant magnetic field. Here you can see a spectrum from water phase, from metronidazole, from free nuclei of metronidazole, its polarization levels from metronidazole, and here spectra from organic phase. So also we measure T1 relaxation time, and T1 relaxation time was really good, like 12 minutes for nitro group of metronidazole. It's also really good because such a long T1 relaxation time may be useful for potential in vivo studies. Also, we checked cell viability for metronidazole solution, and we showed that cell viability remains largely unchanged after incubation with metronidazole solution that was obtained using the cache-SABRE approach. So our solution is biocompatible. It's really important for potential applications. So, and about perspective, actually this work paves the way for studies of nitroimidazole metabolism in vitro and in vivo using a combination of hyperpolarization and magnetic resonance spectroscopy. And we had publication about it. So I would like to express my gratitude to all my colleagues from Novosibirsk, especially from my supervisors Dudari Burueva and Igor Koptyuk, and for my colleagues from Germany, Andres Schmidt and Ivan Trofimov, and my colleagues from China, Wei Huang and Huan Liu. So thanks for your attention. I would be happy to answer to your question. So I am almost on time.
Yeah, thank you for the wonderful talk. Are there questions from the audience?
Yes, I can ask a question. Sergey, thank you so much. That was really interesting and fascinating, and quite a bit what you did during your PhD. That's very impressive. I have many questions I could ask you for hours, but maybe if we go to, I think it was the first FIPSA example, just a small, very specific question. What catalyst did you use?
As a rule, we used, I can write, rhodium complex like this, NBD, code, birth, like this.
Okay, and what solvent?
What?
What solvent? And what solvent?
Solvent. Okay. Acetone.
Acetone. Okay.
Yeah.
Did you ever try in water? Did you try aqueous?
No, because for aqueous we need to use aqueous soluble catalyst, and we don't have it. It's one reason. Another reason, anyway, if we can use water soluble catalyst, it would be super hard to remove this catalyst after procedure. But for this catalyst, there are a lot of works of Glogler group that shown we can remove this catalyst from final solution.
And did you said that the T1 on the format is likely a reason for the short the low polarization. Did you measure T1 on the format?
Yeah, we measured T1. It was like 20 seconds for format.
Okay. And where you I think you performed the bubbling in Altadena style outside in an NMR tube or in a reactor, or how?
NMR tube. Always NMR tube.
Okay, thank you. And it's interesting that you did as well the N15 polarization with FIPSA. How did you what biological function or thingies can you expect, and what was the T1?
What was T1? Actually, we didn't measure T1 for nitrogen, but as a rule, T1 for nitrogen is more or less long, especially in comparison with carbon 15, maybe more than several minutes. So I guess the main problem actually in chemistry.
Okay, I mean, it always depends on the chemical environment, right? But if I see the nitrogen, maybe you can pull up the structure. I think there were no hydrogens close by, but many exchanging sites, right?
Yeah. Yeah, probably. But for example, for metronidazole, T1 in organic phase with catalyst, so it's not so good for relaxation, was like several minutes, and 12 minutes for aqueous phase without catalyst. Catalyst also really important for relaxation.
Is there a specific reason you didn't measure the T1 for the nitride? Low SMR or something?
No, it's ongoing work.
Okay.
Like this year.
That would be very interesting. I would be curious to see. Maybe it's in the literature. I'm just not aware of it. I don't know.
Yeah. Cool. Actually, it's really interesting.
Maybe I'm permitted a last question, Martin, before maybe some others would like to ask. Did you estimate what doses you would need to give of the antibiotic to detect it in vivo in tissue?
What doses you mean volume?
Now, what would be the doses you need to inject into like a human or an animal that it's detectable in vivo? You know what I mean?
Yeah. I understand. Yeah, sure. We need to use bigger concentration that we used for in vivo, and we need to use big volume. I guess for example, for pyruvate, we need to use at least several milliliters and concentration about several hundreds of millimolar. So I guess for metronidazole, more or less same.
Do you have a feeling for if that would be healthy or not?
Healthy. If we will do a purification procedure good, I guess it will be okay.
Thank you so much. Really impressive work. Thank you.
Are there more questions from the audience? Why do you have so much T1 times, so long T1 time for metronidazole?
You mean 12 minutes?
Yeah, these 12 minutes T1 time.
Yeah. Actually, it was also a surprise for us, but first of all, it's connected to this pure solution without catalyst and with, I guess, unique chemical structure of metronidazole and especially nitro group. So like some symmetric environment. But actually, as I know, we can expand T1 relaxation time for nitrogen. For example, there are several works about it, but with natural abundance, it really depends on magnetic fields, and for magnetic fields of benchtop is really long.
Are there more questions? If not, then I would say thank you again, Sergey. It was a really impressive talk, and like Jan said, a lot of work. It's really amazing. With these words, I just close the seminar, and thank you again for the talk.
Thank you for invitation.